Have you ever stopped to think about how your phone, your laptop, even your smart fridge can all connect to the internet and just talk to each other? It's pretty wild, right? Well, it's all thanks to a shared set of rules. And today, we're going to dive into the two fundamental blueprints that make our entire digital world possible: the TCP IP and OSI models.
I mean, really think about it for a second. An Apple iPhone that was made in China has to talk to a Google server sitting in the United States running on completely different hardware and software. How in the world does that actually work? Well, it all comes down to creating a universal language for all these different devices.
So here's our game plan. First, we'll talk about why we even need this universal language. Then, we're going to look at the big theoretical blueprint, the OSI model, and compare it to the super practical TCP IP model that actually runs the show. We'll see how they map together, and then, for the really cool part, we'll see why this stuff is absolutely essential for any security analyst out there. To put it simply, without a shared set of rules, the internet would be total chaos. Imagine if every car manufacturer invented their own traffic laws. It would be a disaster. In networking, these rules make sure that data gets from point A to point B reliably, and it doesn't matter what kind of device you're using.
And that's exactly what a networking model is. The best way to think of it is as a shared architectural blueprint. You know, just like builders use a blueprint to make sure the plumbing in a new house actually connects to the city's water supply, developers use a networking model to make sure their new app can connect to the entire global internet. All right, let's start with our first model, the OSI model. Now, you should think of this one as the big, comprehensive, almost academic ideal. It was designed way back in the late 70s by these big standards organizations that were trying to create the perfect universal plan for how any network should work, long before the internet as we know it even existed.
And this perfect plan is incredibly detailed. It breaks down the whole complicated process of communication into 7 distinct layers. And here's the key. Each layer has one very specific job, and only one job.
Okay, here they are, all 7 of them, from top to bottom. Now look, don't freak out, you do not need to memorize all these names. The big idea here is to just appreciate the structure. For example, take a look at the transport layer. That's layer 4. Its whole job is reliability, making sure your data gets there in the right order with no mistakes. And right under that, the network layer is basically the internet's postal service. It figures out the best possible route for your data to take. The genius of this is that you can have a problem on one layer and you can fix it without wrecking everything else.
So at the very top, we've got the application layer. This is the part you actually see and touch. When you open up your web browser, Chrome, Firefox, whatever, you are directly interacting with layer 7. It's the human-facing part of the network.
And then you go all the way down to the bottom and you hit the physical layer. This is the complete opposite. It's got nothing to do with software. It's all about hardware. We're talking about the actual copper Ethernet cables, the fiber optic lines, the radio waves for your Wi-Fi, all the raw physical stuff that carries the ones and zeros.
Okay, so while that 7-layer OSI model is this beautiful, perfect theory, it's not actually what the internet was built on. See, while all the academics were designing OSI, developers were in the trenches actually building ARPANET, which was the precursor to the internet. And they created a more pragmatic, streamlined cousin, the TCP/IP model. They totally won out because it was practical, it was developer-driven, and honestly, it just worked.
And really, its simplicity is its greatest strength. Instead of 7 super specific layers, the TCP IP model just condenses the entire communication process into 4 functional layers.
And here it is, the TCP IP stack. You'll see some familiar names, but it's way more compact. It's less about rigid theoretical rules and more about just getting the job done. This is where all the protocols you've actually heard of live. Things like HTTP for web browsing up in the application layer, and TCP and UDP for sending data in the transport layer. This is the real foundation of the internet we use every single day.
So, we have the theoretical 7-layer blueprint, and we have the practical 4-layer building. So how do they relate to each other? Well, this is the real aha moment, where everything is going to click into place.
Okay, this is it. This is where it all comes together. Just look at how these two models map together. See at the top, those first 3 OSI layers, application, presentation, and session? They're all kind of squished together into one single powerful application layer in TCP IP. Makes sense, right? Then as we go down, transport and network, well, they have almost direct counterparts. OSI's network layer just gets a new name, internet, in the TCP IP world. And then at the very bottom, all the really physical stuff, the data link and physical layers, they get bundled up into the network access layer. It's just a perfect illustration of taking a complex theory and streamlining it for the real world.
All right, so we've got a theoretical model and a practical one. Why in the world should anyone, especially a security analyst, care about a theory that isn't even fully implemented? Well, this is where the OSI model becomes an incredibly powerful tool.
So yeah, if the internet really runs on the 4-layer TCP IP model, why are we always talking about the 7-layer OSI model? Well, the answer in a single word is diagnostics. The OSI model gives security pros this amazingly detailed, granular way to troubleshoot problems. If your internet is down, is it a physical problem with the cable at layer 1? Or is it maybe a software configuration issue in your browser way up at layer 7? This model gives you a logical checklist to just go down the list and pinpoint the exact source of the problem. It also helps them understand how an attack moves through a network and figure out exactly where to place their defenses, like a firewall, to be the most effective.
This quote just sums it up perfectly. It's not about being theoretical. It's about having visibility. This framework lets an analyst look right through all the complexity and see the underlying structure of the network. It makes it possible to spot weird anomalies and threats with incredible precision.
And that brings us to a final, pretty critical question. When you have this layered view of our digital lives, everything from the physical cables under our feet to the apps on our screens, where does the greatest danger actually lie? At which layer are our networks, and by extension all of us, most vulnerable? We're going to explore that very question as we dive into the specific tools that operate at all these different layers. So, in our next explainer, we're going to break down the hardware that brings these models to life: routers, switches, and firewalls. We'll see you then.